All right, guys, moving into the second half of 13.2, we're going to start talking about the unit circle in just a second. But before we do that, this is something that's pretty darn important. And if you were to ask any Algebra 2 student after they got done with the class, why is it that you struggled with trig? They will probably tell you because I didn't memorize this information as well as I should have. So I can't stress this strongly enough, guys. Get this in your notes, write it down really big, put a box or a circle or a little drawing next to it and study this stuff. We're going to revisit and kind of redefine special right triangles, which we talked about in 13.1. So in these two boxes, guys, we have the only two special right triangles that exist. A 45, 45, 90 here on the left, so named for its three angle measures, and then a 30, 60, 90 over here on the right. Now, do not write down what I'm about to do right here, guys, but in the last section, what we talked about is naming one of the legs here x, and then the second leg would be x, and the hypotenuse would be x times the square root of 2. And then, in the 30, 60, 90, we named the short leg x, we named the long leg x times the square root of 3, and the hypotenuse was 2x. All of that is still true. However, what we're going to start talking about in just a second is a specialized case of these triangles here where the radius or the hypotenuse, this is important right here, the hypotenuse is always going to be equal to 1. So what we are going to do, and this I would recommend that you guys put in your notes, is put a 1 right here for the hypotenuse and then work to figure out what this x is right here. So if this stuck for you guys before, what we're going to do is to go from hypotenuse back to a leg in a 45, 45, 90 triangle, we're going to divide both sides by the square root of 2. So x is going to equal 1 divided by the square root of 2. This is a weird, ugly, irrational number, and we don't like having irrationals, radicals, in the denominator. So we multiply both sides by root 2, or I should say we multiply by root 2 over root 2. And in the numerator, 1 times root 2 just becomes root 2, and in the denominator, root 2 times root 2 is 2. So that right there, guys, becomes the value. I'm going to get rid of this because it's just going to make this a little messier now. This missing leg here is the square root of 2 divided by 2. And then, of course, whatever you got for one leg in a 45, 45, 90 triangle, you get the exact same thing for the other leg. So these three numbers here, guys, root 2 over 2, root 2 over 2, and 1. That's the group of numbers that I need you guys to have memorized here as quickly as we possibly can here, okay? So I'm going to get rid of all of this right here and make sure then that we're seeing the important stuff. Root 2 over 2 and root 2 over 2 are the legs of a 45, 45, 90 triangle, and 1 is the hypotenuse. Now, again, there's lots of 45, 45, 90s out there. It's still true, if you look back at a homework problem from the last section, that if this side over here was, 13, this side would be 13, and this side would be 13 root 2. So not every triangle that's a 45, 45, 90 in the world has these three side lengths, but when we're on the unit circle, the hypotenuse is going to equal 1, and that means that if the hypotenuse is 1, these are the lengths of the two legs. So let's memorize that as quickly as we can. Same concept over here on the 30, 60, 90, guys. If the hypotenuse is 1, let's think about where we go from there. To go from the short leg to the hypotenuse, from here to here, we always multiplied by 2. So to go backwards, we would divide by 2. And what's 1 divided by 2? 1 divided by 2, otherwise known as 1/2. So that's how long the short leg is in a case like this. Let's see if I can move that box a little bit. That's better. Nope, that did not work. Come on. There we go. And now, how do you go from short leg to the long leg? We multiply by the square root of 3. So we would take 1/2 times the square root of 3, and that just becomes 1 times the square root of 3 is root 3 all over 2. So the long leg here is root 3 over 2. And guys, this is a group of numbers that you need to have memorized as well. In a 30, 60, 90 triangle, on the unit circle, where your hypotenuse is 1, your short leg is 1/2, your long leg is root 3 over 2, and your hypotenuse is 1. Now I'm going to come back to those in about 5 minutes, and those numbers you're going to see why those are so important in just a second. All right, guys, on to the really fun stuff in this section right here. Trigonometric ratios on the unit circle. So let's begin, before we get too complicated right here, with defining what we mean by this phrase right here, unit circle. And that's this definition written for you right here. A unit circle centered at the origin. So this point right here is right where the x and the y-axes intersect, and that's the center of your circle, and the radius is equal to 1. 1 what? 1 unit. Doesn't matter whether we're talking about inches, centimeters, miles, feet, kilometers, whatever. So a radius of 1 unit means that we're dealing with a unit circle. And this diagram that you're looking at right here, guys, looks a little bit scary when you see it here at first. All right, but this is one that I made actually on AutoCAD a long time ago right here, and I'm going to try to be as consistent as I can with you guys and show you this diagram as many times as I can here, and while we're working through it, explaining what all of that junk that's behind it means. So we'll get to that a little bit later. I don't want to overwhelm you with this right now, but this is what we mean by a unit circle. Its center is at the origin. Oop, that's not, there we go. Center is at the origin, and its radius is equal to 1. Okay, so with that in mind, let's see what we can do now with this unit circle. What's a little scary sounding about this, oh wait, I lied, is that in a minute, we're going to start doing problems like this. Without a calculator, we're going to be able to find the exact values of sine and cosine and tangent of 16 different angles that are located on that unit circle. But before I do that, we're going to make this table right here. We are going to rethink and in a way redefine sine and cosine and tangent. Now again, this is not going to change or contradict anything that you guys have learned a year ago in geometry or just a couple of days ago in section 13.1, but it is going to enhance that. It is going to modify that just a little bit. So what am I talking about, guys? This first column right here, I'm going to fill this out in purple. The first column where we're going to try to redefine sine and cosine and tangent in a triangle, this is exactly what you guys are used to. This is where you probably want to think about SOHCAHTOA. All right, everybody, what's the definition of sine? Once again, that is the opposite leg divided by the hypotenuse. What's the definition of cosine? That would be the adjacent leg divided by your hypotenuse as well. And what's the definition of tangent? TOA and TOA is going to be the opposite leg divided by the adjacent leg. Now I want to say this again loud and clear. All of these definitions that you've learned in the past are correct. They still work. And in a lot of cases, thinking about sine and cosine and tangent this way, in terms of SOHCAHTOA, will work for you just fine. But I will warn you, there are certain angles on a circle or on the unit circle that don't actually form a triangle. So there is no opposite leg or adjacent leg or hypotenuse. So this line of thinking can get you in trouble then, and that's why we want to come up with these two definitions right over here. A new definition of sine and cosine and tangent on a general circle. So let me show you guys what it is that I'm talking about right there. When we are on a circle, I'm going to draw just a really simplified version of what's going on here. So, maybe this is a unit circle. It actually doesn't have to be, but just any circle that looks like this. And some random point located on that circle, I'm going to put it right up, I'll put it right over here there, guys. That ordered pair, we're just going to generically call x, comma, y. X is our x coordinate, and y is our y coordinate. And what I'm about to do next is to make a triangle out of that one point right there. We're always going to connect the origin here, the center of our circle, to that point in that spot right over there. And then we're always going to drop an altitude. There's a word from geometry. A line segment that goes from this point straight down to the x-axis, forming a right angle. And so when we did that, guys, we've just formed a right triangle from this one point located right here. And let's talk real quickly, guys, about what the side lengths are within that triangle. If this ordered pair right here has the coordinates x, y, I want you to think about what that means. If you were plotting that point, you would start at the origin, and to plot the point xy, you would go x units to the right, and then you'd go y units up. That means that this length right over here on the bottom is x, and then this length here going up the side would be y. The hypotenuse of this triangle, you'll notice, is the radius of that circle, even though I drew a really bad circle right there. So this piece is going to be r. And then the last thing to talk about right here, the angle formed between the initial side of the angle and the terminal side. This angle right here is what we call theta. And guys, if I haven't formally defined this yet, and I'm not sure that I have, theta is a letter in the Greek alphabet, Theta. And all it is a letter, and just like most English letters, we use it in math for a variable. But in higher levels of math and science, theta is the variable we use the most often to represent an unknown angle. So with this in mind, if I were to ask you guys, all right guys, with that labeling system in mind, what's the sine of theta? Well, you guys would all go right back to this column right now because it's all you know, and that's going to be perfectly fine right here. And you're going to tell me that sine is opposite leg over hypotenuse. So from theta, this is the angle where I'm standing right here, my opposite leg is y, and my hypotenuse is r. So the sine of angle theta is going to be y over r. And you know what? That's correct. So that's what we're going to put into this table right here, guys. The sine on a general circle is going to be y divided by r. Okay, there's a reason we're kind of redefining it rather than opposite leg over hypotenuse, and I'll show you that a little bit later. How about the cosine of this angle right here, guys? Cosine is once again adjacent leg over hypotenuse. Here's your adjacent leg, here's your hypotenuse. So cosine is going to be x over r, and that's what's going to go in this cell right here, x over r. And tangent, just like before, guys, the tangent of an angle is opposite leg over adjacent leg. Here's your opposite leg, here's your adjacent leg. So the tangent of theta is going to be y divided by x. So y over x is our definition now of tangent. So these are what we're going to call the x, y, r definitions, everybody, of your three trigonometric ratios. Sine is y over r, cosine is x over r, tangent is y over x. However, I'm going to go one step further with you guys and try to redefine these same ratios here on a unit circle. And let's go back. What was our definition of a unit circle? Any circle centered at the origin with a radius of 1. So if we go back and we look, wrong way, if we go back and look at what's going on right over here, if we know that we're on a unit circle, we know that our radius is equal to 1. So now instead of y over r, this would become y over 1, and of course anything divided by 1 is just itself. So if you're on a unit circle, guys, sine is just y, or the y coordinate of whatever point you're at. Now the same thing happens right here. Cosine is x over r, but on a unit circle we know that r is 1, so this becomes x over 1, which is just plain x. So I'm actually going to get rid of this here. That should make that a little bit easier to understand, I think, guys. If we're on a unit circle specifically, sine is just your y coordinate, cosine is just your x coordinate. Unfortunately, guys, nothing simplifies right here on a unit circle. The fact that r is 1 doesn't do anything for us for the value of y over x, so that one needs to stay where it is right there. So these are some new definitions of sine and cosine and tangent relative to what we call circular trigonometry. And in just a second, I'm going to show you guys why those definitions are important. So with all that in mind, let's get working on this first problem right here. And I've got 4 examples I want to do with you. And for each one, we're going to find sine and cosine and tangent of each one of these angles. All right, guys, let's take a look. 60 degrees. So the first thing we're going to do, I'm going to make this diagram just a little bit bigger. The first thing we're going to need to do is locate where a 60-degree angle is on our unit circle. So, like we did at the beginning here, I'm going to draw my initial ray, which is always pointing out to the right, and then a 60-degree angle from that. Well, this is going to be in the first quadrant, and it's just going to go 60 degrees. Now, you wouldn't know this unless I told you, but that's what some of those goofy dots right there are representing. This first dot right here, guys, is 30 degrees. The second one is 45 degrees, and the third one then is 60 degrees. Then, of course, we've got 90 degrees right here, and I tell you what, I guess since this is our first time going through it and actually using this diagram, let's keep going. I'm hoping you guys can see that there's symmetry to this all over the place. From 60 to 90 is a 30-degree jump. Here's another 30-degree jump right here. That's going to get us to 120. Okay, another, let's see, from 45 to 60 was 15 degrees, so another 15 degrees here gets us to 135, and then this would be another 15-degree jump to get to 150. 30 more degrees gets us to 180, and now I'm hoping you guys see the patterns right here. We could keep going with the 30s. This would be 210. We'd add another 15 right now to get to 225, another 15 to get to 240, another 30 gets us to 270 degrees. Another 30 degrees is 300. 15 more is 315 degrees, 15 more is 330, and another 30 degrees to take us home gets us to 360 degrees, which of course is right where we started. I should have written that, and this angle right here is both 0 and 360. So the 60-degree angle, once you guys have this memorized, it's going to be pretty easy to spot. That's what this little dotted line is for right here, guys. You shoot it up through that kind of hollow point right there, and I'm going to fill that in now, guys, and this is what a 60-degree angle looks like on the unit circle. But now, we're going to make a triangle out of this. From that point that I just colored in right now you can see why these vertical dotted lines are here. We drop an altitude straight down until it hits the x-axis, and we have formed a right angle right there. And if we go a little bit further, you guys know even more. This angle right here is 60 degrees. Which means we're dealing with a triangle with a 60-degree angle and a 90-degree angle, which means this up here must be a 30-degree angle. We are dealing with a 30, 60, 90 right triangle here, guys, in the first quadrant. So that's kind of cool, but now the fun part. How are we actually going to find the sine and cosine and tangent? Well, what we're going to do, guys, is we are going to label the coordinates of this point right over here. And to do that, now we're going to go back to what we wrote down a while ago, which was this information right here. Now, in this problem, we're dealing with a 30, 60, 90. So the side lengths here, 1/2 was going to be the short leg, √3/2 was going to be the long leg, and 1 was going to be the hypotenuse, because we are on a unit circle with a radius or a hypotenuse of 1. So let's go back to where we were right here, guys. I'm going to fill in those 3 side lengths now in this diagram. The radius, or the hypotenuse we said, is 1. The short leg is 1/2, and the long leg is the square root of 3/2. Those numbers work with the Pythagorean theorem, but the one thing that we knew had to happen was that the radius had to be 1. So that tells us something, guys. The coordinates of this point right here, this dot we're talking about right there, the x-coordinate of that point is 1/2, and the y-coordinate going up right here is the square root of 3/2. And as ugly as those numbers are, we need to get used to them. Now that you know this, the rest of this problem is going to be pretty easy. This is your x-coordinate, and this is your y-coordinate. And of course, right here, we know that the radius is equal to 1. Maybe I should have written that over here somewhere, guys. So what I now know is that our x-coordinate there is 1/2. Our y-coordinate is square root of 3/2, and our radius is 1. So when I ask you guys, what is the sine of 60 degrees? What I want you to do is go back to this table right over here and realize that since we're on a unit circle, sine is just your y-coordinate. And what is our y-coordinate at this point? I can see it right here. I can see it right here. I can see it right here. Y is the square root of 3 over 2, and that is the sine of 60 degrees. Not that hard once you get everything set up at the beginning right here. How about the cosine of 60 degrees, everybody? Let me go back again. Cosine on a unit circle is just equal to your x-coordinate. Well, here's my x-coordinate. Here's my x-coordinate. Cosine of 60 degrees is 1/2. And lastly, this one's a little bit tougher than the last two, the tangent of 60 degrees. So tangent, and it doesn't matter whether we're on a general circle or a unit circle, it's always the same, is y divided by x. So tangent, this gets a little ugly, guys, is the y-coordinate, the square root of 3 over 2 divided by the x-coordinate, which is 1/2. And we don't ever like to divide by a fraction. So what we're going to do instead is take that numerator, root 3 over 2, and multiply it by the reciprocal of the denominator. Dividing by 1/2 is the same thing as multiplying by 2 over 1. And what happens here? Those 2's cancel each other out, and we just get the square root of 3. So there's the sine of 60, there's the cosine of 60, and it took some doing, but there's the tangent of 60 degrees. And that's the way that you guys are going to be asked to come up with sine and cosine and tangent, not of any angle out there, but of what I call the sweet 16. All of the 16 angles on that unit circle that will give you a special right triangle when you graph it. And you guys are going to be asked to come up with sine and cosine and tangent of those angles there without using your calculator. This is how you do it. It's a little scary at first. So let's do another example here, guys. Let's do a 135 degree angle this time around. Okay, and again, I'll make that a little bigger and a little easier to see. Okay. Where is a 135 degree angle? Initial side points straight out to the right, and 135, well, let's think, guys, this gets us to 90. We would need to go another 45 degrees. So we're talking this angle right here. I'm going to fill in that dot, and I'm going to go ahead now and draw my radius that always goes back to the origin every single time, and then we always drop an altitude down to the x-axis right here. And there's your right angle, and here's the right triangle that we've formed here by drawing this 135 degree angle. Okay, so now, guys, we're in the second quadrant, and our reference angle, I'm hoping we see this one here already, the angle between the terminal side and the x-axis is going to be 45 degrees. So I see a 45 and a 90. That means this is a 45 degree angle as well, and we're dealing with what special right triangle here? 45, 45, 90. So let's label our side lengths, guys, going back to this. On the unit circle, when you know that your hypotenuse has a length of 1, the legs are both root 2 divided by 2, and the hypotenuse is 1. So I'm going to label here, each side is going to be the square root of 2 over 2. That's it on the left, and it here as well, root 2 over 2, and the hypotenuse is 1. So the coordinates of this point then, guys, now let's think about something though. The x-coordinate here in the second quadrant always has to be negative. We're actually moving to the left of the origin, so this number here is actually negative root 2 over 2. In the second quadrant, your x-coordinate has to be negative. But your y-coordinate, we're going up above the x-axis, that's still going to be positive root 2 over 2 in the second quadrant. And again, once more, our radius is equal to 1. So let's get rolling here, guys. The sine of 135 degrees. Now, once again, I don't expect you guys to have this memorized yet, but here you go. On the unit circle, where your radius is 1, sine is just equal to your y-coordinate. So the y-coordinate is given right here, everybody, root 2 over 2. Now, I should have said this earlier. If you were going to go to your calculator right now, you could ask it, what is the sine of 135 degrees? And it's going to give you a value of 0.707 blah, 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 blah. That's not what we wrote down. But if you were to then ask your calculator, what's the decimal equivalent of this expression right here, and type in the square root of 2 divided by 2, it'll tell you 0.707 blah, blah, blah. These two values are exactly the same, which tells you we're doing this one right. Okay, something weird happens now. The cosine of 135 degrees. So let's go back to these new definitions again. There you go. Cosine is x over r, but if you're on the unit circle and radius is 1, then cosine is just your x-coordinate. So the x-coordinate here is given to us by this value, negative root 2 over 2. So this kind of opens up the door to the world of possibility here, guys, that trig ratios can be negative. Now, you're going to like this one, though. The tangent of 135 degrees. Tangent was the hardest of the three back here a moment ago when we did 60 degrees. But in this case, guys, it's not as bad. The definition of tangent is y over x. Here was your y coordinate, so that's going to be root 2 over 2 divided by this x-coordinate right here, which is negative root 2 over 2. And I'm hoping you guys see it. We're dividing a number, even an ugly number like root 2 over 2, by its own opposite. And any number divided by its opposite, like 5 over negative 5, is just going to get you negative 1. And that would be a pretty easy one to type into your calculator and see. If you were to type in tangent of 135 degrees, it'll tell you the answer is negative 1. Okay, so that's how you handle a 135 degree angle. So in both of these cases, what I'm hoping you guys are seeing here is that we simply draw the angle, label the sides, figure out what x and y and r all are, and then we simply use these new definitions of sine, cosine, and tangent to figure out those values there for each of those ratios. Let's do a third one here, 270 degrees. So the initial, again, I'm going to make that a little bigger here. Okay, and this is a point I've been waiting to make here, guys. Okay, the initial position, straight out to the right, and 270 degrees might sound familiar to you. This is 90, this is 180, 270 takes you right down here. So the terminal side of this angle points straight down, and this, let me go back to red here, is what a 270 degree angle looks like. Now, the weird thing is, what happened on the last two problems is that after I located this point, I drew my radius, I dropped an altitude, and that created a triangle. In this problem, it was a 45, 45, 90. In this problem, I found that, I went here, it was a 30, 60, 90. What kind of triangle are we forming here? Well, we're not. Because from this point, if I draw my radius, well, that's the same side I just drew. And if I dropped an altitude back to the x-axis, it's that same piece again. Guys, this is what we call one of the 4 quadrantal angles. All right? And the weird thing about quadrantal angles is they don't form triangles. So if you were to think about sine here as opposite leg over hypotenuse, which would have worked for you here and here, it doesn't work for you here because there is no opposite leg. There is no adjacent leg. There is no hypotenuse because there is no triangle. All right, so that's why the quadrantal angles are a little bit funny. But that doesn't mean that these angles don't have a sine, cosine, or tangent. We handle this the same way. We say, all right, guys, what are the coordinates of that point right there? The x-coordinate, everybody, starting from the origin, this point didn't move left or right at all. Its x-coordinate is 0. And its y-coordinate, we are going straight down from the origin. And remember, guys, this is a unit circle with a radius of 1, so our y-coordinate is negative 1. So x is 0, y is negative 1, and the radius, just like always, is positive 1. So as soon as you know these 3 pieces of information, the rest of this should be relatively simple. the sine of 270 degrees. Again, if we don't have it memorized yet, sine is equal to our y-coordinate. That's it, guys. And the y-coordinate right here is -1. Okay, cosine of 270 degrees. Cosine is equal to our, there we go, x-coordinate. So the x-coordinate here is 0. And here's a fun one now. Tangent of 270 degrees. That's equal to y divided by x. So that's a -1 over 0, and I really hope we know this by this point, guys. Anything divided by 0 is undefined. So it is possible, you guys, that tangent could be undefined anywhere that your x-coordinate is equal to 0. And of course, that happens along the y-axis. Okay, so once we get the hang of this, this actually goes pretty quickly, but this example right here illustrates why we had to learn these new definitions right here in this column and this column for sine and cosine and tangent, because SOHCAHTOA only works in a triangle, which is what we wrote right here. It doesn't work when there is no triangle, which happens at the quadrantal angles. And I think I had one last one for you guys, and then we're done with this one. -210 degrees. You know what? I changed my mind. I don't want to do that. I'm going to make this -150 degrees. Here's the reason why. -210 is a second quadrant angle, which we did already. -150 is something different. So here you go. Drawing the angle, here's the initial position straight out to the right, and because it's negative, we're now going clockwise. This would be 90. That would be 120, 135. This one right here, guys, is -150 degrees. So we're talking about this point right here. Let's draw the radius going back to the origin, and let's draw the altitude then to the x-axis. And this is what we're dealing with here, everybody. So our -150 degree angle, we would draw it like this. That gets us now into the third quadrant, where we haven't been yet today. And our reference angle right here, once you guys get the hang of using this little chart, this little diagram, you're going to know what it is without even thinking very hard. That's a 30-degree reference angle. 30, 90, this is a 60-degree angle. So we're dealing here, everybody, with a 30, 60, 90 right triangle. So back to what we wrote down a long time ago now. Here we go. A 30, 60, 90 on the unit circle is going to be given with these three numbers right here. The short leg is 1/2. The long leg is √3/2. The hypotenuse is 1. And the sooner we have that memorized, the faster we're going to get through these problems here. So the short leg is 1/2. However, I'll come back to that in a minute. The longer leg is √3/2, and the hypotenuse is 1. But I want to remind everybody, we're in the third quadrant. And in the third quadrant, both your x and your y values have to be negative. So that's actually a -1/2, which I was about to say you might know because we're going down from the x-axis. The √3/2 is negative as well because we're going left of the origin, or left of the y-axis. So what do we know, guys? Our x-coordinate right here is negative √3/2. Our y-coordinate is -1/2, and our radius, just like always, is 1. In case you're wondering this, it is definitely possible, you can see it right here, for x to be negative. It's possible for y to be negative, but guys, it is never possible for r to be negative. R will always be +1 if you're on a unit circle, which is the way we're drawing this. So let's knock out these three questions, guys. The sine of -150 degrees. Okay, fourth time we've done it now, guys. Sine is just your y-coordinate, which is right here. The sine of -150 degrees is -1/2. Cosine of -150 degrees. Cosine is just your x-coordinate. That's this number right here, which is -√3/2. Got it. And then the tangent of -150 degrees. Tangent is defined as y/x. So this one now, guys, I'm drawing my big fraction bar here. My y-coordinate is -1/2 divided by my x-coordinate, which is -√3/2. And again, we don't like to divide by a fraction, so we're going to multiply by its reciprocal. This is negative 1/2 times a negative 2 over root 3. Okay, what happens here, guys? The 2's cancel. Oh, a negative times a negative makes a positive, so that's nice. And we end up with 1 over the square root of 3. But we can't leave that radical in the denominator, so we have to rationalize. We'll multiply top and bottom by the square root of 3. And that gets us, in the numerator, 1 times the square root of 3, which is the square root of 3, and in the denominator, root 3 times root 3 is just 3. All right, so guys, there's your exact answers for the sine of negative 150, the cosine of negative 150, and the tangent of negative 150 degrees, all of which we did without using our calculator. Now, guys, this is scary stuff. I would expect you to have your head spinning right now, but I want you then to start that homework slowly, one problem at a time, watching this video or looking at your notes as you're working through the first couple of problems, and hopefully you're going to see that, okay, all I'm doing is I'm drawing the angle, I'm locating this point, I draw my radius, and I drop my altitude, and then I recognize what kind of triangle I'm dealing with. It'll either be a 30-60-90, or a 45-45-90, or a triangle that doesn't really exist at all, if it's what's called a quadrantal angle. And then from there, you just got to figure out your x and your y coordinates. At that point, r is always going to equal 1. And then we just have to go back to these new definitions we wrote down on the unit circle here for sine and cosine and tangent. All right, everybody, work slowly through that. Ask questions as they come up, but that's how we handle coming up with these sine, cosine, tangent values of any one of those sweet 16 angles. Good luck, everybody, and let us know when you have trouble.